This is Adel from Oz Engineering. In this video, we'll go through an Ansys Charge Plus example that demonstrates the ESC simulation workflow using a parallel plate capacitor. This example is available in the software. Let's start by creating the two electrodes. For that, I'll draw a circle and I'll give it 900 millimeters diameter. Now if we go to design one and expand it, we can see the surface and we can copy and paste it to create the second electrode. Here I want to create 80 millimeters spacing between the electrodes, so I'll move the first electrode 40 millimeters up and I'll move the second surface 40 millimeters down. So now we have our electrodes with 80 millimeters spacing. We can go to surface, right click on it, and click rename. I'll rename it top electrode. And for the second surface, I'll rename it bottom electrode. Next, we will assign materials to the electrodes. So let's go to the EMA 3D tab, then Materials. Here we will create an isotropic material. I go to General, and I'll change the electric conductivity to 100 meg Siemens per meter. Now using the Surface Select tool, let's select the top and bottom electrodes and click Complete. In the next step, we'll define the problem space by initializing the domain. The domain boundary should fully encapsulate the model. So let's click on Domain. Here I'll expand time, lattice, minimum, maximum step size. Let's keep the minimum and maximum values as is, and let's change the step size to 10 millimeters for X, Y, and Z. This setting correlates to the mesh size. I'll also change the number of divisions. Here make sure the product of divisions does not exceed the number of logical processors on your machine. Now let's go to boundary and change the boundary condition on all directions to mirror 1 each field. And I'll change the end time to 40 nanoseconds. And click Complete. Now we will define a current source by creating wire geometry. So first, let's add a point on the domain. So here I'll click Position, and I'll change the X position and Y position to 0. And I'll click Create and Complete. And we can see this point centered on the origin on the negative C domain boundary. Now let's create second point, this time on the positive C domain boundary. So I'll change X and Y to 0, and here 120. Click Create and Complete. And we can see our second point here. Now let's go to the Design tab and add a line to connect the positive Z domain point to the center of the top electrode. And then we'll add a second line to connect the negative Z domain point to the center of the bottom electrode. Now we will define the source excitation. So I'll go to the EMA 3D tab and add a current source. Using the line select tool, we can select the first line and click complete. Here we need to make sure that the arrows on the current source line are pointing from the domain boundary to the surface of the electrode. Now let's do the same for the bottom electrode. And here I will change reverse current direction to true to make sure the arrows are pointing to the right direction. Now let's define waveforms for the current sources. Here we'll select the linear ramp signal. Here I'll set the amplitude to 1000 amps and the time to peak to 2 nanoseconds. Now in the simulation tree, let's right click on linear ramp 1 and click copy to duplicate it. And I'll drag and drop linear ramp 1 under current source 1 and linear ramp 2 under current source 2. In the next step, we'll define the arcing region for this geometry. So under the EMA 3D tab, let's click on breakdown region, expand properties, bounce. Here let's set minimum x to -470, minimum y to -470, and minimum z to -40. For maximum x, 470, for maximum y, 470, and for maximum z, 40 millimeters. I'll change the relative humidity to 0%, and I click complete. And here you can see the breakdown region highlighted. Now we will define a voltage and an animation probe. For that, I'll first hide the breakdown region. And here, let's click on voltage probe and select the midpoint of the top and bottom electrodes. Now to define an animation probe, we need to create a plane. So let's go to the Design tab and draw a 945mm square. Now using the Move tool, let's center the plane on the origin. And then we'll move it down 40 millimeters. Now let's rename this animation plane. Then let's select the EMA 3D tab and add the animation probe. Here we'll select the surface and set the probe type to normal electric field. And let's click complete. Now we need to mesh and run the model, so I'll click on the mesh button. Here you can see the mesh. And then I'll click Start to run the simulation. Once the model is solved, we can view the simulation results. So let's go to Results and right click on Voltage Probe 1 and select Plot. So here we can see the voltage probe result, and we can edit this plot by right clicking, Configure, Chart, and here we can change the plot settings. As we can see in this plot, around 32 nanoseconds, a sharp voltage change occurs. This is caused by the air breakdown between the electrodes. Now to view and export the results from the animation probe, right-click on Animation Probe, Generate Animation. Let's hide the mesh. And also to properly view the animation plane, I will hide the top electrode. Now let's go to the Legend tab and let's change the opacity to 70%. And here I'll export the animation as a GIF. In this GIF we see a charge built up on the electrodes, followed by a breakdown that initially occurs at the edges of the plates. The breakdown time, shown in the bottom right corner of the GIF, is 32 nanoseconds, which aligns with the voltage probe result. In this video, we went through the Ansys Charge Plus Paschen test demo. Thanks for watching, and see you in the next video.